Okay, good morning. Homework is due today, so if you haven't brought it up yet, bring it up either right now or after class and get it to me. We have another homework assignment over Chapter 6 due a week from today. We'll be talking a little more. We talked some about that. I think we'll talk a little more about it either today or Monday. Keep reading Chapter 6, especially sections 11 and 12 for Monday. And exam 2 is coming up not this Wednesday, but a week from Wednesday. So I'll be getting practice exams out to you sometime, hopefully early next week. So that's the game plan for the rest of the month. Now, what I wanted to talk about today is continue talking about the Hodgkin Huxley model. And remember, last class, first we developed the model mathematically, and then what we wanted to do was we looked at the voltage clamp idea of the experimental method. So let me just quickly review the voltage clamp, and we'll look at a few more pieces of data from that. So here's the idea. You have a nerve, axon, and hopefully you've all had a chance to look at that nice video with Alan Hodgkin doing the voltage clamp measurements. You stick an electrode in there, and it's attached to a voltmeter, and outside is grounded. So it's really measuring the voltage across the cell membrane. And you also have another electrode that can pass current. It's hooked up to a current source, which you can control the current. And then the idea is that you're going to basically watch the voltmeter, and whenever the voltage deviates from the voltage you want it to be, you're going to adjust the current in order to keep that voltage constant. That is, you're going to clamp the voltage. It's a voltage clamp. And what you're going to want to look at is the amount of current per unit S. If it changes over time, that gives you an idea of how the conductance of the membrane changes over time. So, here was classical type of voltage clamp data, where you have V as a function of time. This is the voltage that you specify. So there's minus 50 to plus 50 in millivolts. Rest potential is down here. And at time 0, 5, 10 in milliseconds. So you specify this voltage. Remember, I said you're watching the voltmeter and adjusting the current. It all happens too fast to do that by hand, so there's a feedback circuit that does that. You feed what voltage you want to apply into the feedback circuit. Initially, we have resting potential, so we don't have to do anything. Just the voltage just sits at rest. And then at time 0, we're going to say, okay, the voltage is going to jump up to plus 15 millivolts. Now this is what we talked about last class, so still looking at what we've done last class. So you specify this, and then the question is, what current does the feedback system have to apply? So here's the current, and it's going to go from about 1 to minus 1, and that is milliamps per centimeter squared. Just make sure that's milli. That's what it has in my notes. And the current that has to be applied. Well, when it's at rest, you don't have to apply any current because the nerve sits there at rest, so there's no current. When it jumps up suddenly, there's a huge capacitive surge that only lasts when the voltage is changing. With this voltage, is going to change very quickly, so you get this giant capacitive surge. Then it comes back to 0. What happens when you depolarize? The M gate in the sodium channel opens. H is already open at rest partly. M opens, sodium rushes in, an inward current, mainly by sodium, that turns on. Then it's going to slowly turn off because the H gate, which is slow, closes upon depolarization. So it's this depolarized potential H is closing, turns it off, and the N gate opens up upon depolarization, but it's also slow, and you get the slow potassium current, which stays constant. So the current looks like that. This is where we got last class. So are there any questions about how to interpret that voltage clamp measurement that we got to this point last class? Okay, let's try a different one. We're going to do the exact same experiment with V, 50, minus 50, and 0, 5, 10. But now we're going to jump it up to a higher voltage. We're going to go all the way up to 50 millivolts. Okay, so this will be a test sort of how well you understand the system. We want to know what the current is doing. These are all functions of time. Well, we know initially it's at rest. It doesn't require any current. There's still going to be a big capacitive surge. If anything, it's bigger than it was. What happens now? We bring the voltage up to 50 millivolts. What is the sodium current going to look like? Think about that. What was the expression for the sodium current? Well, you had the G bar Na, which was the peak sodium conductance. That just sort of scales this whole problem. You had M cubed H, which are going to act similar to what they acted here, because M is going to open upon depolarization. H was already open partially. So you're going to have the gates are going to open up. But you're going to have V minus V Nernst, the Nernst potential for sodium. What was the Nernst potential for sodium?
35.
Actually, a little higher.
Oh, 50.
It was 50. So if I ramp the current up to 50, what's going to be the sodium current? 0. If you're sitting at the Nernst potential for that ion, then you don't have any current, even if the gates are wide open, because you're in equilibrium. The diffusion to want to come in is equalized by the electric field pushing it out. So the current, basically this current disappears. You still have a potassium current, because its Nernst potential is down at minus 77. So if anything, the potassium current just got bigger. Not because of N necessarily, but because it's really the voltage minus the Nernst potential, which is at minus 77, so the voltage difference between V and the Nernst potential just got bigger. So that current still comes on, and if anything, it's a little larger. So it's going to look like this. So what this shows you is this is one way to figure out what the experimentally what the Nernst potential is. They can estimate it by the equation we derived, but they can find it in the experiment by just finding where their current disappears during the voltage clamp. Okay? Yes?
But wouldn't it initially be negative? Like, it wouldn't... Oh, never mind.
Yeah,
automatically...
That was a sodium current that went negative. The potassium current's going the other way. So let's do one more. Let's do V 50 minus 50 and 0, 5, 10. And now we're going to start at rest, and we're going to jump it up even above that. We're going to jump it up to, say, 75 millivolts up high. Now we want to know what the current is. 1 minus 1. Well, again, no current when it's at rest. Big capacitive spike. Now, it depolarizes, so M gate opens up. H was already partially open, and it's slow. So the sodium channel opens up, but now you're sitting at 75 millivolts. So what's the sodium current? It changes sign. Instead of driving sodium in, when you open the gates, the electric field, the electric effect dominates over the diffusion, and even though there's more sodium out there, you drive sodium out of the cell. So you get this thing, which then falls off as H closes, and then you get the potassium, which is even bigger still. So it looks something like that. So you see, you get a lot of information from this voltage clamp. You can get an idea of how much the current is. You can get an idea of sort of G sodium bar and G potassium bar by looking at the sizes of these currents and therefore their conductances. You get information about where the potentials are, the Nernst potentials for these different ions. You get a lot of information about how they behave. So this is the kind of experiments that Hodgkin Huxley did. They would voltage clamp at all sorts of different levels and basically trace out how the currents responded. And they show a lot of that data in their paper. All right. Now, they still haven't shown you how they get the H gate dynamics, because H is a little strange. How do you know that H is partially open at rest? And does that really make any sense? So here's another experiment they did. This is an even more complicated one. We'll start with V. 0. Actually, what I'm going to do is I'm going to move 0 all the way out here. 5, 10. This is all time in milliseconds. So we're going to do the same experiment, but we're going to have it sit here at rest a long time, and then we're going to jump it up to 15. Okay, this looks like exactly this experiment. I just moved the axis around. So you really get exactly the same result. Current, because I haven't done anything except shift the axis. So I get my spike, I get my inward, and I get my outward. Now I'm going to do a little trick. Let me see if I have any colored chalk. Here's a piece of yellow. This might do. I'm going to try a new experiment where I'm going to say we start here at 0, and then I'm going to give it a negative pulse down to minus 85 millivolts from minus 65. Over, and then I'm going to jump it up to 15. So it's still 15. So I've changed the experiment a little bit. I've hyperpolarized pre-pulse. What happens? Well, remember when not much happens during the hyperpolarization pulse because the sodium current M gate's closed and it's still closed, even tighter when you hyperpolarize. The potassium current, well, it may change in a little bit, but you're down near the potassium nurse potential, so it's not going to have much effect. The leak current's real small. Basically, you get very little effect, maybe a slight change, but very little effect with this pre-pulse. It doesn't look like it does anything. But then, what's going to happen when you jump it up to 15? Well, what you got, and this is a little bit of a surprise for them, is they got a current that looked like this. Big current. And then it felt pretty much similar over here. How do you interpret that? Well, apparently this pre-pulse did something to the sodium to kind of make it larger. It didn't have any effect on the potassium. The way to interpret this is the H gate. Remember, the H gate at rest was partly open. This pre-pulse, what the pre-pulse did is it completely opened the H gate. The way to think about it is this. Here you have your H infinity curve that we drew last class. This is the value that H is going to after a long time. This is a function of voltage in millivolts. And the curve at rest was partly open. So the curve looks sort of like this. It closes upon depolarization. Now, if you hyperpolarize, what you do is you basically go from this point down at rest down to this point. And remember, this hyperpolarization was actually held for a long time. So they hyperpolarized and held it long enough for H to reach its new H infinity value. And its new H infinity value was up here somewhere. H just got closer to 1. It opened wider. And that's why H is really slow, but you gave it enough time to completely open. Then when you jump, in a sense, the sodium channel has been supercharged. This H gate is open wider than it would have been. So when M opens up, the H gate is just super wide open, and you get a large sodium current. So what Hodgkin Huxley could do is they could put various sized pre-pulses on their voltage clamp experiment, and they could basically trace out what this H infinity curve was and get some idea of how it behaved. So that's how they got some of the information they needed to understand the H gate. So you see there's lots of different experiments you can do with the voltage clamp. And by putting that all together and then fitting it to finding some functions to fit their data, they were able to come up with their mathematical model. So that is a little bit about voltage clamp. You guys aren't asking many questions these days. Are there more questions? Any questions about voltage clamp experiments? Yes.
How do they know that? And you know how it's like partially open and then it opens fully, like during depolarization. How do they know that's not like two separate?
That's
Like one's like always open, like the leak almost, and then one like end is like closed and then open.
yeah. I will. I'm not absolutely certain, but I'll guess. And I'll guess is that if you do these experiments without sodium in the bath, so you completely knock this out, and then you did some of these pre-pulse experiments, I think you could probably get that information. But it's not real clear because you're really looking at how N-abate comes in after long times. Yeah, it's actually a good question. How do you get the N for essentially? See, N is going to be, let's think about it here. N infinity curve is going to be looking like this. It's going to, it's a active, it's a gate that, no, and will be just the opposite. It opens upon depolarization. So I guess what they did is they could do the, here at rest, and then they could look at, yeah, hyperpolarized pulses is what you need to trace out how N is behaving down here. What I'm not sure about is if they were looking at very small potassium currents during the pre-pulse, or if they were getting that information out here. That I'll have to think about a little bit and look at the paper. All right, other questions? Okay, well, let's go on and look a little bit more at the Hodgkin Huxley model and see if we can understand better. Okay. Now, if you look in the Hodgkin Huxley paper, you will find a equation for M, differential equation. It looks a little different than what I wrote in class. So what I wrote in class was dm dt equals m infinity minus m over tau m. What you'll find in the Hodgkin Huxley paper looks a little different, and I'm going to show you how they're actually very similar. And I think this is almost the same as one of your homework problems. So it's sort of a gift here. But dm dt in Hodgkin Huxley was written as alpha m, a function of voltage, times 1 minus m minus beta m times m. Now why they chose to write it in this way, I don't know. But this is what they did. Let us look and see how you can make this look the same as the equation I gave you. First thing we'll do is we'll say, okay, there's going to be a term that doesn't depend on m, so I'm just going to write it, I'm going to abbreviate alpha sub mv as just alpha. I'll get that term, and then there's two terms that depend on m linearly, so I'll go minus, one of them is alpha, and one of them is beta, times m. So this is really the same as what we had before, alpha minus alpha m minus beta m. Now I'm going to do something that's really kind of strange. I'm going to multiply top and bottom by 1 over alpha plus beta. So essentially I'm doing this. I'm multiplying the whole thing by 1 over alpha plus beta divided by 1 over alpha plus beta. So I'm multiplying by 1. What does this do? This term becomes alpha over alpha plus beta minus this term, alpha plus beta cancels, you just get m. And now there's a denominator down here that has 1 over alpha plus beta. That's dm dt. Let's compare this equation to this equation. And you can just read it out. What's m infinity in terms of alphas and betas? Well, m infinity is this thing. Yeah. Alpha over alpha plus beta. And tau m is just 1 over alpha plus beta. So there's a relationship between the two. So Hodgkin Huxley's equations, and they actually give the equations for alpha and beta in their as a function of voltage in their paper. They don't give m infinity and tau m directly as a function of voltage. Let's see if the units actually work. Here's the m dt. M's dimensionless, so this is 1 over time. That means alpha and beta have to have units of 1 over time, or 1 over seconds. In their paper, it was 1 over milliseconds. Well, alpha and beta have 1 over milliseconds, so what's the units of m infinity? Well, it's 1 over milliseconds divided by 1 over milliseconds. M's dimensionless, as we knew. It had to be dimensionless. Here, 1 over milliseconds, but it's in the denominator. Tau, time constant, is milliseconds. So it all works out. So this is when you're going to be doing some of the homework problems, and you want to figure out what m infinity and tau m are, especially m infinity and the others. You'll use the equations that Hodgkin Huxley gave for the alphas and betas. All right. Now, I promised you last class that I would answer this question about why Hodgkin Huxley didn't use just m, but used m cubed. And they didn't use just n, but they used n to the 4th. So, let me show you an example. Let's focus on the potassium current. Imagine you took the sodium out of the solution and you just had potassium current. So we know the potassium current, the way they wrote it was gk bar n to the 4th v minus vk. And what we really want to know is y to the 4th power. Okay, so here's what we're going to do. We're going to imagine you did a voltage clamp experiment. Okay, why don't you just hand it to me? I'm
very sorry to have interrupted.
Okay. We're going to do a voltage clamp experiment where you're going to up the voltage and you're going to depolarize the voltage and hold it there. If you do that experiment and you look at the current, what you're going to see, and what we've seen before, is the current, here's time 0 where we jump, so the current was 0. You've taken the sodium out of the solution, so there's no sodium current. The current's going to turn on like this. And the important thing is it's kind of got this sigmoidal S shape. It starts really flat because it ends really slow, and then it turns on. Okay, so that was the shape of the potassium current. I'm going to put IK just because we took the sodium out. So this is essentially all potassium. And that means the conductance. Basically, if you're holding voltage constant, this is really a plot of the sodium conductance. Okay, now, let us look at what N is doing. Equals N infinity minus N over tau N. In a voltage clamp experiment, N infinity and tau N are just constants. We don't have to worry about them changing because it's clamping the voltage, so by very definition, those are constants. So you can solve this. I'm not going to go through the whole solution. Just let me remind you, if this term wasn't here, it looked like a decaying exponential. This term is here. At long times, you expect to go to some constant value. So you expect some exponential, maybe with a constant term. This is the solution. N infinity plus the initial value right at the start when you turn the voltage clamp on, minus N infinity e to the minus t over tau N. Yeah, you could plug that in. You can find out it works. If t is really large, the decaying exponential, this whole term goes away. You just N infinity, as you'd expect. If t was 0, e to the 0 is 1, N infinity cancels that infinity. It's the initial N, which is what you'd expect. Let's plot this. We plot this, so plotting N. Here's the initial, here's the final, and here's 0 when the thing turns on. So initially, you turn on the current. This is an exponential. It approaches N infinity, but it approaches it like this. That's the way the exponential behaves. Now, here's the thing. This turns on abruptly and now goes to a constant slope going up. It's not a sigmoidal shape. It's a turning on of this exponential. This has this sigmoidal shape. So you're not going to be able to fit your data with this equation for n if you just used n by itself. But Hodgkin Huxley found that if they raised n to some power, then instead of starting off linearly, it started off either at this quadratic or even a quartic equation. It started off n to the fourth would look something like this. Okay? It would start slowly and turn on sigmoidally. That's why they used n to the fourth. How they chose the fourth as opposed to some other integer, they just curve fit their data. Found a function that looked like the closest fit to their experimental currents. And one other thing is the nice thing about using n to the fourth, n goes from 0 to 1. Okay, n equals 0 is the same as n to the fourth, which are both 0. And when n equals 1, n and n to the fourth are the same, or 1. So it's really mapping still 0 closed, 1 is open. It just changes, sort of the way it changes as a function of time, so that it's got more of the sigmoidal shape. They did the same thing with the sodium current, and that's how they got their m cubed. So, there's absolutely no fundamental theory behind those. It's curve fitting. Okay, so I fulfilled my promise, my campaign promise, to show you why it was n to the fourth and m cubed. Now let's continue on. And if you've read the Hodgkin Huxley paper, you'll recognize some of the figures from the paper. If you haven't, I'll just try to recreate them here on the board. Okay. The whole model they derived was all based on their voltage clamp data. So in the paper, they then used the model to predict the voltage clamp data. And of course it worked, because that's how they made the model, with the voltage clamp data. So if that didn't work, they would have just been they would have been incompetent. But the model correctly predicted what the voltage clamp experiments were. But then they said, let's go model the action potential. Because the model didn't use anything about the action potential itself in creating it. So if the model could now explain the action potential, then they've actually made some good progress. So here's their figure 12. And they're plotting V versus time. Let's see, 0, 2, 4, 6, so on. And V is going to be plus 50, minus 50. And you start down here at rest, at minus 65, and their model gets the correct resting potential. And at time 0, you somehow raise the voltage, let's say maybe by 10 millivolts. So you just go in there and you artificially, as if there's a stimulator, raise the voltage up. And then you start calculating and see what's going to happen. Well, what does happen? As you raise the voltage up, you start that vicious cycle. You raise the voltage up, M opens up. M opens up, sodium rushes in. Sodium rushes in, it raises the voltage inside even higher. And you get this sort of rapid, explosive upstroke. And that's indeed what you see if you look at the action potential in nature. And it stops when it gets up here about plus 50, because in part, that's the sodium Nernst potential. So eventually you drive it up to plus 50, and now there's nothing driving sodium in anymore. Then H gate turns on, or closes off the sodium, N opens up even more. It drives the action potential back down. And it actually drives it down below rest, because N is wide open for a while. And you get this slight hyperpolarization until it eventually comes back to rest. And you get an action potential like this. And if you do the experiment, you get almost exactly the same thing. And one of the nice, powerful things about Hodgkin Huxley's paper is it would show a theory curve and an experiment curve. And you can look at them, and you can see that maybe they're not superimposable, but they are very similar, essentially telling you the same information. So they were able to predict the action potential quite nicely. That was one of their triumphs. Another thing they did is they looked at figure 14. They wanted to look at high temperature. Now for high temperature, they had to put temperature into their model. And it does enter into the Nernst potential slightly. But the main place they put temperature into their model is these gates alpha and beta. They had 6 of them altogether, 3 alphas for M, N, and H, and 3 betas for N, M, and H. And they assumed that those increased with temperature. They had some function, but the exact function doesn't matter. These increased with temperature, so the rate constants increased with temperature. And then in problem 42 of your homework, no, maybe you don't have it. Maybe it's not part of the homework. Problem 42 asks, how does M infinity and tau M change with temperature? Let's say you change alpha and beta. They increase with temperature in the same way. Let's just, for the moment, think of it as a linear increase. Well, how did M infinity depend on alphas and betas? It's right back in your notes. Alpha over alpha plus beta. So if alpha and beta both increase temperature the same amount, they're in the numerator and the denominator, they'll cancel out. M infinity does not change the temperature at all. However, tau M was 1 over alpha plus beta. So if alpha and beta increase with temperature, tau M will decrease with temperature. Actually, yeah, tau M is a time constant, so things happen faster. So what they did when they calculated the action potential at different temperatures, they found that you get essentially the same shape, but it happens a lot faster. I don't like that. It's all over in a millisecond, basically. And when they did the experiments, because that was an easy experiment to do, all they have to do is change the temperature of their dish. They found that, yes, the temperature change really reflected just these gates here. All right, so that was another figure from their paper. Now, this is even more interesting figure. I will try to draw this best I can. It's kind of a complicated figure. This is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. Temperature in time in milliseconds. And I'm going to be plotting voltage 50 minus 50 in millivolts. And the first thing I'm going to do is I'm just going to fire an action potential. So it's going to look just like this plot up here. A regular temperature sits at rest. I raise the voltage a little bit, then I let it go, and it goes up, and then it comes down, and then it hyperpolarizes a little, and eventually goes back to rest. Okay, now, here's what they did next. They said, suppose we don't fire just one stimulus. We don't think of this as a stimulus if we start the action potential. Suppose we do a stimulus, and then later we do another stimulus. What's going to happen? All right, so they went out to about 4 milliseconds. I mean, initially, everything's identical. At 4 milliseconds, they gave another stimulus. And they found that, boy, even if they stimulated really hard to drive this voltage up, all it did is came back down. There's no action potential. There's a stimulus artifact, but no action potential. The nerve's refractory. Remember why the nerve's refractory? The H gate got closed by this action potential. The depolarization closed it, and it's slow, and it didn't have time to open back up. If you go to 5 milliseconds and you stimulate, you get an action potential. It's kind of wimpy, but you get one. If you waited 6 milliseconds, then you could fire without much stimulus, and you get almost nice action potential. And if you wait like 7 milliseconds, you get something that's essentially identical to what you had before. So what you're doing is you're tracing out the refractory period. Here, no matter how hard you stimulate, and it's true also earlier, you couldn't get another action potential. So this is what's known as the refractory period. So the refractory period, essentially, this time. And then here, you get an action potential that's kind of wimpy. And that's the nerve is thought to be relatively refractory. You still get an action potential, but you have to stimulate really hard to get it. And out here, it's back to like it's purely at rest. So the refractory period is completely over and everything works. So they did these calculations and they compared them with the experiments and they worked. Now here's one interesting thing. If you look at their calculation experiment, it didn't actually look like this. It looked more like this. You know why their calculations look like that? Well, remember, this is Huxley and his hand crank calculator. This is taking forever to do these calculations. So once he saw the action potential, he said, I don't want to spend another week tracing out how it returns to rest. I don't learn anything from that. So he just stopped. And he'd go do another one. So this really reflects the technology of the time. They had to know whether an action potential fired. But once they knew, who cares what else happens? So they have a nice picture of theory. It looks like this. An experiment doesn't cost anything to get the whole curve. And it really shows that they were able to explain the refractory period using a model that was based entirely on voltage clamp data. Here's another figure of theirs. This also has a story to tell us. Figure 21. Again, we're going to be plotting V versus time. But now we're going to have kind of a different scale. This is going to be minus 65, minus 60, minus 55, minus 50, and so on. So the voltage scale is just drawn a little differently. You're initially at rest. So you're initially here at rest. And at time 0, we're going to raise the voltage up and see what happens. Suppose you raise the voltage up by 2 millivolts, from minus 65 up to minus 63. Well, that wasn't enough to start that positive feedback loop underlying the upstroke of the action potential. So if it doesn't start the positive feedback loop, it just goes back to rest. So I'll put 2 down here, representing a 2 millivolt rise, and it does nothing. And you can even raise it up in another experiment up to about minus 60, which is 5 millivolts. And it comes back and it does nothing. If you raise it up 6 millivolts, it looks like it's trying to do something, but it finally goes back. You increase it a little more to 7, and it does whoom, and starts taking off. And it actually, since this scale is only up to minus 50, the curve goes up to the ceiling, up to the plus 50, and you get the full-blown action potential. So as you think of this as turning on the stimulus knob, you're slowly turning your stimulus up. You're saying nothing, nothing, nothing. Turn it up just a little more, and bang, you get an action potential. This is what's called the all or none action potential. This is the way action potentials work. You either get one or you don't. You either start that positive feedback and the whole thing goes up to sodium nurse potential, or you don't start the positive feedback and it just goes back to rest. This looks like their experimental paper, their experimental data, and they did their calculations and it showed exactly the same thing. So not only could they learn about refractory period, they could learn about this all or none stimulus. So it's kind of important to remember, nerves work by either firing an action potential or not firing an action potential. Those are the two choices. Okay. One more of Hodgkin Huxley's figures I want to share with you. So let's go and get rid of this. I didn't write down the number of the figure, but I'll be able to check it out. Okay, well, first a little philosophy here. If you're making a model of something, making a mathematical model, well, if the model can predict the stuff that you made the model to predict, that's what it's supposed to do. So you should be able to predict this voltage clamp experiments. And the whole model was motivated by predicting action potentials, even though they didn't use the action potential. So the fact that it predicted the action potential behavior, not terribly surprising, but still good. But there was this little weirdo behavior called anode break excitation, which nobody really understood, and it almost looked like an experimental artifact. Almost. The model explained it perfectly. So let me see if I can show you what anode break excitation is. Here you have V, 50, minus 50, let's go down to minus 100 millivolts, versus time. This will be 0, 5, 10. You start at rest, minus 65. And remember, during the voltage clamp, they put on that hyperpolarizing pre-pulse. Let's do that in this experiment. So you're going to essentially voltage clamp it down to minus, say, what did I write on there? Minus 115. Ooh, that's pretty, okay, well, I got to draw this better. And at time 0, you're going to release the voltage clamp and just let the action potential do whatever it wants. Let the nerve do what it wants. So essentially you turn the hyperpolarizing current on, held it on a long time, and then released it. What's going to happen? Well, I'll show you what happens. Here's rest. It starts heading back to rest. But it overshoots rest. And if you overshoot rest enough, you can get up to where you reach the threshold. Remember the all or none action potential? If you raise it by about 7 millivolts, it will fire. You get an action potential. Not that high. And this is called anode break excitation. It's anodal because you're hyperpolarizing. Most stimuli, you want to depolarize. Depolarize it until you get to the threshold and fire action potential. This hyperpolarizing. It's break because nothing happened until you turned the voltage clamp off, until you turned your stimulus off. And then you got this action potential. Let's see if we can, and they did this experimentally, and they saw this, and they did it with their model, and they saw this exact same thing. So let's see if we can understand what's happening. Okay, so when you hyperpolarize, what do? Well, it goes, you're holding it a long time, so everything goes to steady state. M was already closed at rest. It stays closed because it can't go any lower than 0. H was partly open at rest. So let's see, H infinity versus V. Here's rest, and it looks something like something like this. Here it was at rest. It closes upon depolarization, but on hyperpolarization, it opens up. So H infinity, by the time you got to here, was larger. It supercharged the sodium current. You didn't get an action potential because M was still closed. But H was bigger than normal. And infinity curve against V, rest, was something like this. And here it had been partially open, and now it was open even higher. So sodium or potassium current was a little larger than before. Sodium current wasn't larger, but it was sort of primed to really fire. The leak was still out there with a Nernst potential somewhere around minus 45 or something. So as the action potential, as the voltage headed back to rest, when it got to rest, the potassium current was a little larger than usual. The leak current was the same as always because the leak doesn't have any gates. But remember, the resting potential is usually a competition between the leak and the potassium. And now the potassium is supercharged, so it went up, I've done this, okay. More, I made a mistake. It hyperpolarized. We hyperpolarized by the stimulus. It's going this way. You're turning off the potassium. I'm sorry. So when you get up to here, The leak's the same as the leak was always, but the potassium is smaller than usual. So essentially it's driving you to a voltage, sort of a resting voltage above your normal resting voltage. And that's enough to get you up to where you start the positive feedback, and because H is larger, it's primed and ready to go, and you get a great reaction potential. So H is bigger and N is smaller by this hyperpolarization, and it's just enough to cause this anode break excitation. And again, they saw it in theory, they saw it in experiments. Odd little result that really indicates that this model, it must be getting something right if it can predict this weird behavior as well. So, let me just tell you a little story, because I misdrew this curve and I had it going up above the sodium nurse potential. Well, the funny story is that Hodgkin Huxley weren't the only people who were looking at action potentials. There were some people in America, Curtis and Cole, who were looking at action potentials, and somehow, by some artifact, I don't think anybody quite understands, they were seeing action potentials up to around 100 or 150 millivolts, depolarized. So they're seeing these real tall action potentials. And if you read the Hodgkin Huxley paper carefully, you'll see they spend a lot of time trying to explain away this weird data, because if the action potential really was going up to 150 millivolts, their whole model is wrong. It's above the sodium nurse potential, so it just doesn't make any sense. But nowadays we think that Curtis and Cole in the United States just must have screwed up. That's pretty much the only explanation. So Hodgkin Huxley got the Nobel Prize, and Curtis and Cole went down. That's kind of a footnote. Okay. Let us look now a little bit at some of the homework problems. Any last questions about the Hodgkin Huxley model? Essentially, we've gone through their paper. We've gone through what the model predicts. Let us look now at some of the homework that you're going to be doing. Okay. Problem 41. That one is in the homework. Problem 41. Okay, this one is essentially asking you to find out what M, H, and N are at rest. We've been talking about those. M's closed, H is partially open, N's partially open. Let's see if you can actually calculate them. Well, how do you do that? Well, first of all, you remember, for instance, M is going to equal M infinity at rest because it's at rest. So it's been sitting there in steady state. And that's equal to alpha M over alpha M plus beta M. And Hodgkin Huxley give you all these equations. They're also in your book. In fact, the Hodgkin Huxley paper, remember, has that different definition of the voltage. It's 0 at rest and depolarized is minus. So I would strongly suggest you use the equations in the textbook. Otherwise, you're going to have to go through and do the conversions properly to use the equations in Hodgkin Huxley's paper. But, so you're going to have a bunch of equations for these. For instance, beta M. The equation looks like 4 exponential of minus V over 18. Actually, it's V minus V rest over 18. That's what it looks like in the book. If you're sitting at rest, because we asked what was the resting value of M. Well, V minus V rest is 0. So you'll get e to the 0, which is just 1. So beta is going to be 4, 1 over milliseconds. Okay, that was an easy one. The other equation for alpha M is a little more complicated, but you can calculate these. And then you can put them in this equation and you can calculate what M infinity is. That's what the problem's asking you to do. And you can get H the same way. You got these complicated expressions for beta H and alpha H, but you can calculate them, put in the resting potential for V. You're going to always see V minus V rest goes to 0. You're going to then be able to get alpha H over alpha H plus beta H, and also for N. So, problem 41 is just calculating. You want to have the experience of actually calculating those one time. Remember, you won't have to memorize and know all these equations for an exam, but I do on the homework where you can just look them up in the book. I want you to go through and calculate them. That's problem 41. Okay, if you find yourself doing anything too complicated, you're probably doing 41 wrong. Problem 43 is always kind of a hard one for the students. This is again on the homework. Let's remember the Hodgkin Huxley model, but we're going to write it for steady state, so I'll ignore the capacitive term because we're going to be only looking at steady state. We had an m cubed h v minus vna plus gk bar n to the fourth v minus vk minus plus g leak v minus v leak. Now, what I want you to do is I want you to calculate the resting membrane conductance. At rest, if you put on small, say you stimulate with a small current, you're going to change the voltage change a little bit, and it's going to have an effective conductance for the membrane. And that's what you want to get. So, the way you do this is to realize that at rest, I is 0. So when so you really know that I equals 0 at rest. So that means if you take resting potential minus VNA here, resting potential minus VK, resting potential minus V leak, and you use the values you just calculated for alpha, beta, M, H, and N, you will get something very close to I equals 0. Now, what happens if you take V to be the resting value plus some little delta V that's going to be small that represents a deviation from rest? Well, for V you can put this in for here, here, here. So what you're going to get is kind of a complicated equation, but remember that if V was exactly rest, all these things are going to add up to 0. So you're going to have a bunch of terms that have the V rest in here. And those are all going to give you 0. And then you're going to have some terms that have a delta V added in. You're going to end up getting I is equal to some complicated thing times delta V. And all the terms that had the V rest are going to go to 0. And this complicated thing right here is the resting membrane conductance. So that's the general way to approach that problem 43. Make this assumption, use the fact that at rest the current's 0, and get an expression. You just have to fill in what's inside the bracket. I'll leave that for you to do. One hint, for this problem, you don't have to worry about M, H, and N changing with voltage. You're going to assume that these deviations are so small that the gates don't change that much, and you're just going to mainly look at what the conductance is at rest. So it's kind of a limiting problem. If you go down to small enough delta V, the gates won't change, but you'll still get the current proportional delta V. Okay. We still got a few more minutes. Let's look at some of the other homework problems, because that's what you're going to be faced with. Problem 6, or chapter 6, problem 1. Okay. We talked a lot about Hodgkin Huxley model, but problem 1 is actually more basic. It's just some basic reasoning here. Suppose an action potential in a 1 micron diameter unmagnetic fiber has a speed of 1.3 meters per second. We haven't talked about the speed of action potentials. All we've talked about is how action potentials behave across the membrane. But in the next class or two, we're going to explain how if you have a long axon, the action potential can actually propagate down the axon with a certain speed. So let's just assume that happens for the moment. And you're given the speed. Estimate how long it takes a signal to propagate from the brain to the finger. So this is estimate, which means you just try to roughly see how long it is. So estimate how long it is from here to your brain. And you're given the speed, so you can calculate the time. I mean, it's just speed is distance over time. And that's going to give you a time. And then the funny thing about this problem is that you're going to do it for two types of fibers with different speeds. and you're going to speculate on the significance of these results for playing the piano. Oh, that's random. If you're playing the piano, especially if you're sort of sight reading some music, you look at the music and then you got to tell your fingers to move. And that takes, there's a certain delays in there. And if those delays are too long, you can never play any fast music because you see it and then your fingers respond 3 seconds later, you're not going to be able to play music. But if it's instantaneous message transmission from your eyes to your brain to your fingers, you can play anything as rapidly as you physically can move your hand. So the question is, how fast can these signals go? And the examples, the speeds given in the problem are sort of typical for the fastest speed is typical for sort of your fastest fibers that move your fingers. So you can get an idea of what's the time delay and whether that's significant or not for trying to do very rapid motions. So that's problem one. The actual calculation is almost trivial, but it's something to think about. Problem two is another one of these where it's not too complicated. The median nerve in your arm, that's the nerve that goes up your arm and carries most of the nerve fibers back to your brain. Has a diameter of 3 millimeters. It consists of only the nerve consists of only 1 micron diameter unmyelinated axons. How many axons are in the nerve? So the idea is you have a certain nerve, which you're given the radius, and you're also told that it's just full of these small axons. This is what the nerve actually is, a bunch of nerve axons. Incidentally, this is why I told you the nerve action potentials were all or nothing. But you can grip an object with various intensities of your grip. And the reason is not because the action potentials are all or nothing, but you can fire 2 action nerves, you can fire axons, you can fire 10 axons, you can fire more, and that will increase the strength. Each axon is all or nothing, but the number of axons firing can change. So you can just basically calculate the volume of the individual axons and the volume of the nerve. You can calculate how many axons it takes. And for 1 micron axons, you get a whole bunch. But if you go up to a really big axon, for instance, if you go up to 0.5 millimeter, you can have something like this. You couldn't fit many axons in there. Now, why would you ever want to do this? Well, as we'll show in a later class, the bigger the axon, the faster the action potential. In fact, that's why the squid evolved to have such big axons. So their escape reflex, where they go whoosh and escape their predator by sort of jet propulsion, that can happen really fast and they can get away. So they wanted the real fast axons. So we have to ask ourselves, do you want fast axons or do you want a lot of axons? Well, you sort of want both. But this problem has you sort of figuring out what, if you make the axons too big, assuming the nerve only takes a fixed space, you just don't have many axons. You can't run a hand with 4 axons. Not only do you have to move various muscles, but you also have to have sensors, pain sensors, heat sensors. You need a lot of axons. But if you need a lot of axons, they got to be small, and then they're slow. We'll talk about myelination, and one of the reasons we have myelinated axons is it sort of gets around this limitation of you can have some small, relatively fast axons if you use this trick of myelination that we'll talk about later. But all you're really asking in this problem is to calculate how many axons can fit for different various sizes. So it's just cross-sectional area in one case over cross-sectional area of the whole thing. All right, so that's problem 2. Obviously, got a few minutes. Let us look at some of the other homework problems. 22. 22 really has more to do with electrical stimulation of experimental electrical stimulation than something we talked about. So let me just tell you, it's a little off the topic, but it's in the homework. Suppose you have an electrode that you place on the body. You're going to stimulate your median nerve in your arm, so you put an electrode on the skin. And usually they're a disc. So it's a disc like this. And the electrode's metal, so it's isopotential. So the electrode has some voltage V0. And it's made out of silver, which is a high conductivity, so it's got some conductivity. If you do that, that's kind of look from the top, from the side, and it looks sort of like this. Okay. If you do that, you'll find, and you pass current through it. What you'll find is that the current is a lot larger out here at the edges, and is fairly small inside the interior. And I actually give you the expression for the current density. And that expression in problem 22 is some constants, but it's got some constants times 1 over r, a squared minus r squared, square root. Yeah, yes. So when a, this is the radius, when the r gets out to the radius, it gets really big, doesn't it? That's why you have these really big currents out on the edge. And when r is 0, you don't have 0 current, you have a smaller current in the center. And this is experimentally what happens. You can actually, if you pass too much current, you can get burns, and the burns will be right around the edge of the electrode because of this edge effect. So the question is, how much total current comes out of the electrode? Well, the total current would normally just be J times A, except J now varies across the electrode. So really what you got to do is you got to integrate J dA. So this is an integration problem. The way you do it is, here's the looking down at the electrode. You divide into strips like this. The current only depends on R, so the current density is the same in this whole little area. What's that area? Thickness, dr, circumference, 2 pi a, 2 pi r. This is r, and this is r, and this is the whole radius a. So what you're going to get is integral of your expression for j times 2 pi r dr. And you're integrating from 0 out to a. So it's a 2D integration, which is a little bit difficult. That's why I wanted to kind of get you started on it. All you're really doing is you're integrating this, which has this function, it's given, times 2 pi r dr from 0 to a. And you'll probably have to look this one up in an integral table, unless you're really super good and know how to integrate that. It's probably, you could do it with some trig substitution or something. I wouldn't remember. I just looked it up in an integral table. And then you get the total current, and since you have it, you're given the voltage, you can get the total resistance of the electrode. So it's a question that has to do with stimulating nerves using electrodes. That is problem 22 in the homework. And we got maybe 1 minute. Let's see if I can do problem 25. Problem 25 is Nernst potential calculation. So we derive the Nernst potential equation. But this is for calcium. Some muscle cells, calcium is really important. So you want to calculate the Nernst potential. So remember, V calcium is going to be Kt over Q times log of calcium out over calcium in. And it turns out cells keep calcium in really low. That's an amazing thing about cells. They just scour the calcium, so the calcium inside is really low. So the Nernst potential is like sodium, but even more so. It's real high. But Q, here's the way you can screw up the problem, is you might put in just the charge of a single ion, but calcium is double plus. So this is twice the charge of the proton for the calcium charge down here. So don't forget that. And then you can then it's pretty much just plug the numbers in there given in the problem, and you get the voltage for the Nernst potential for calcium. We talked about 35 and 28. We're going to talk about those two next week. And I believe 41 and 43 we've all probably already talked about. 41 and 43 were... That's what we started with, yes. So, that's kind of some hints on the homework. You can do most of them. Numbers 28 and 35 will have to wait until Monday before I can give you some hints on those. Otherwise, that's it for today, and I will see you. Have a good weekend. If you haven't had it in your homework, bring it up front.